Hello, everyone. Um, Once again, with you is Ms. Kade Teresiana, and I'm going to take you through sports nutrition. And our first lecture is going to be an introduction to sports nutrition. Sports nutrition is the specialized field of nutrition that focuses on optimizing the dietary intake of athletes and active individuals to support their physical performance, recovery, and overall health. So our focus in sports nutrition is on the dietary intake of athletes and every individual that is active. We need to make sure that they are supported in their physical performance, and after physical performance, they need to recover from that stress, and also they have to make sure that their overall health is good. The primary goals of sports nutrition are to enhance athletic performance, to promote recovery and reduce the risk of injury, to support overall health and well-being, and achieve and maintain an athlete's optimal body composition. Proper nutrition is very significant for an athletic's performance. Why? Because it provides all the necessary fuel, the nutrients, and the hydration that the body needs for energy production, for muscle strength and endurance, for mental focus and agility, and also for efficient recovery. Some of the components of sports nutrition, we have to focus on the energy, the macronutrients. Here we look at the carbohydrates, proteins, and the fats. The micronutrients, that's the vitamins and minerals. We have to focus on hydration and also supplements. What about energy in sports nutrition? Athletes require an adequate intake of calories in order to meet their energy demands, and this can be influenced by a lot of factors such as activity level. The more active an individual is, the more energy that will be required, the body size, and also the training intensity. The higher the body size and also the higher the intensity of training, the more energy the body will require. So balancing energy intake and expenditure is very crucial for maintaining performance and preventing fatigue. How much energy do athletes need? The energy needs of athletes may vary significantly based on certain factors. For example, the kind of sport. The energy requirement of a footballer will be different from the one of a netballer or a long distance runner. The intensity of this exercise and also the body size and also the specific goals. So energy needs are typically and basically measured in kilocalories or calories. And 1 kilocalorie is the amount of energy required to raise the temperature of 1 kilogram of water by 1 degree Celsius. So this is the unit of measure for energy. Athletes must consume enough calories in order to meet the energy demands of their sport and also maintain their body weight and composition. Where do athletes get energy? Like any other individual, athletes obtain energy from three main sources. That is the carbohydrates, the fats, and the proteins. And carbohydrates are primarily the preferred energy source for athletes because they are quickly converted into glucose and they provide rapid energy during exercise. Fats can be used as an energy reserve, especially during low to moderate intensity activity. And they also provide sustained energy. However, proteins play a very minor role in energy production. And this is because proteins primarily are not the body's preferred source of energy during exercise, due to their essential role in muscle repair and growth. And it is the last resort. In case there are no carbohydrates and also there are no fats, that's when the body can resort to usage of proteins. However, in normal circumstances where there are fats and carbohydrates, proteins are never supposed to be used for energy purpose. So how to measure the energy? We can use the basal metabolic rate, and this measures the energy required to maintain basic bodily functions, for example, breathing and circulation at rest, So this is basically the energy requirement during a rest when the body is not physically active for about 12 hours. That's when you measure the basal metabolic rate. And then the physical activity level. This factor accounts for the energy expended during physical activity and exercise. Thermic effect of food, TEF, and this one represents the energy needed for digestion and absorption of nutrients from food. And finally, the total energy expenditure. This is calculated by adding the BMR plus the physical activity level and also the thermic effect of food. This gives you the total energy that is expended during a specific time and activity. Energy balance and energy expenditure. Energy balance occurs when an athlete's energy intake, that is the calories consumed, equals their energy expenditure, that's the calories burned. And this one usually results in weight, maintenance, and balance. And a positive energy balance happens when the intake exceeds expenditure, and this one will lead to weight gain. Then athletes in the growth phases that are trying to build muscle may intentionally create a positive energy balance. Why? Because they want to build the muscles, and when the muscles are being built, they add on the weight. So it's important to maintain a positive energy balance, whereby the calories taken in are more than the ones that are expended. The negative energy balance. When the energy expenditure exceeds the intake, it leads to weight loss. And this is important for athletes that are aiming to reduce body fat. So they may choose to create a negative energy balance so that they are able to lose some weight. Methods to estimate energy needs and energy intake. We can use the Harris-Benedict equation, and this one estimates the BMR that is based on age, sex, the height, and the weight, and also other factors in activity level to estimate the total energy expenditure. The doubly labeled water can also be used for tracking the elimination of isotopes in order to measure the energy expenditure. Activity trackers and apps. These ones are specific applications on devices of computers, on phones, that estimate calorie expenditure based on the activity level, the heart rate, and also other various factors. And the nutrition professionals can also assess an athlete's energy needs through dietary analysis, taking into account their specific sport and the goals. Factors affecting energy requirements and availability. One of the major factors that will affect energy requirements is the sport type. The energy demands will vary greatly among sports. For example, endurance athletes will need more calories than strength athletes. Training intensity. Intense training burns more calories. So athletes with a high intensity workout require increased energy intake. Body composition goals. Those athletes that aim to gain muscle or reduce body fat may need to adjust their energy balance accordingly. Like how we said, when you want to gain weight, you have to maintain a positive energy balance where the energy intake is greater than the expenditure. But if you choose to lose weight, you have to make sure you maintain a negative energy balance where your energy intake is lower than the energy expenditure. Then age and gender. Adolescents and males will require more energy. Cellular energy metabolism. Cellular energy metabolism is the set of biochemical reactions that occur within cells to generate, store, and utilize energy. And ATP is a molecule that stores and transfers energy within cells. It basically consists of an adenine base, a ribose sugar, and 3 phosphate groups. And these high energy phosphate bonds between the phosphate groups, they store the energy, the chemical energy that can be readily released when needed by the body. So this is the major process of energy metabolism. that starts with availability of glucose. And this glucose is converted into pyruvate, and it goes into the hexosamine pathway. And glucose 6-phosphate that comes from glucose may also be converted to the pentose phosphate pathway. And this pathway is important in the synthesis of fatty acids and sterols. Oxaloacetate is an end result of pyruvate conversion. So this one can enter into the Krebs cycle and work in the electron transport chain in order to generate ATP. So the regulation of energy metabolism. The local factors may include changes in ATP or ADP ratios, calcium influx during muscle contraction, and cell pH changes. Availability of substrates including glycogen and fat, and also hormonal factors, for example, adrenaline, glucagon, cortisol, insulin, growth hormone, and testosterone. These are important regulators of fuel metabolism and muscle tissue growth. Let's basically look at these local factors. The ATP to ADP ratio, in this case, we find that changes in the ratio of ATP to ADP within a cell will serve as a crucial indicator of energy status. When the ATP levels drop and the ADP levels are high, this one will signal the need for more energy production, and it will trigger the cellular mechanisms to increase energy production, such as mitochondrial fuel oxidation, in order to replenish the ATP. Calcium influx. During the muscle contraction, calcium ions are rapidly influxed into the muscle cells, and this influx of calcium is very essential for initiating the contraction process. The calcium also regulates mitochondrial activity and oxidative phosphorylation, which is a critical component of energy production. Cell pH changes. A cell's pH level, acidity or alkalinity. The pH can either be acidic or alkaline. This can also cause changes due to metabolic processes. And then accumulation of proteins such as hydrogen ions in the cell causes a decrease in pH. This is a situation of acidosis where there is a lot of acid, and this can indicate increased energy demand. So these changes in pH can act as signals to adjust the energy metabolism and maintain cellular homeostasis. Availability of substrates. Substrates are the raw materials that are used by cells to produce energy. So there are two important substrates for energy metabolism, and these are glycogen and fat. Glycogen is the stored form of glucose that is primarily found in liver and muscle cells. When glycogen stores are available, they can be rapidly converted into glucose through glycogenolysis in order to provide energy during high-intensity activities. And fat is also another substrate that is very important for energy production, especially during prolonged lower intensity activities. And this happens when the glycogen stores are depleted. The body will decide to rely more on fats for fuel. So these fats are broken down through lipolysis in order to produce energy. Hormonal factors. There are also various hormones that play a role in regulating fuel metabolism and muscle tissue growth. For example, adrenaline and epinephrine. This adrenaline is released during exercise and it activates processes. For example, lipolysis, this is the breakdown of fats, and glycogenolysis, the breakdown of glycogen to provide additional energy. And it also enhances the heart rate and increases blood flow to muscles. Glucagon is released by the pancreas and is very important in raising the blood glucose levels by promoting glycogen breakdown in the liver, that is glycogenolysis, and gluconeogenesis. This is the production of glucose from non-carbohydrate sources. Cortisol is also a stress hormone that increases during exercise and promotes the release of glucose into the bloodstream. It also helps to mobilize fatty acids from adipose tissue for energy. Insulin, released from the pancreas, is also a very important hormone that plays a role in regulating blood glucose levels by promoting glucose uptake into cells. And during exercise, insulin levels decrease in order to allow more glucose to be available in the bloodstream for energy. The growth hormone. Growth hormone stimulates protein synthesis and muscle tissue growth, and it also makes it very important for muscle development and repair. Testosterone is an anabolic hormone that also supports muscle tissue growth and repair, and it's also very important during exercise. Fatigue. Fatigue can basically be defined as an increased perceived effort to exert power output and the inability to maintain force or power output, leading to a need to slow down or stop. Usually, fatigue is a way that the body communicates that it is tired, that it has done too much. So it is explained that fatigue has both the central and peripheral components. Peripheral fatigue can be attributed to local muscle factors that inhibit energy metabolism and skeletal muscle. And then central fatigue is more common in prolonged exercise. It's related to the central nervous system, and it can manifest at multiple levels, including the brain, the central nervous system, the neuromuscular junction, and the muscle. Substrate depletion, including the depletion of ATP, phosphocreatine, glycogen, blood glucose, and nutrition, is identified as a factor in fatigue. When the body feels it is running out of the important substrates in order to run its activities, it usually senses and notifies the rest of the organs that it is overwhelmed and tired. So this is the situation of fatigue that we talk about. Causes of fatigue. This fatigue can be caused by accumulation of metabolic byproducts such as protons, lactate, ammonia, reactive oxygen species, and heat. And also, nutrition can influence these fatigue factors. Like specific nutrition strategies, some of these delay fatigue factors such as muscle acidification. Energy metabolism. Key energy metabolism enzymes may include the PDH, this is pyruvate, dehydrogenase, and PFK, phosphofructokinase. So these enzymes play a pivotal role in glycolysis and the citric acid cycle, and are essential processes in energy metabolism. Energy pathways in sports. During sports, the body utilizes several energy pathways to generate the necessary energy for the different physical activities. So these pathways are often classified into three primary systems. We have the phosphagen system, that is the ATP phosphocreatine system, then the glycolytic system, that's the anaerobic system, and the oxidative system or aerobic system. So the choice of which energy pathway predominates depends on the intensity and the duration of the exercise. The phosphagen system. The main fuel here is the creatine phosphate and adenosine triphosphate, that is ATP. That's why it's called the ATP PCR system. So the duration of energy, this one occurs mainly during very short bursts of high intensity activity, about 0 to 10 seconds. For example, sprinting, weightlifting, and jumping. So these are very short bursts of intense, high intensity activities. So during this first phase, you find that the ATP PCR system is applied. During the initial moments of the intense exercise, the body will rely on stored ATP and creatine phosphate for immediate energy. But when this ATP becomes depleted, the creatine phosphate can regenerate ATP and provide a short burst of energy. The weightlifter explosive power. You find that weightlifters require high energy and force that is generated very quickly. And it highlights that explosive power is related to muscle mass and how effectively different muscle fibers are activated. It also explains how muscle fiber activation varies with exercise intensity, from type 1 fibers during light exercise to all fiber types during intense exercise. So this concept of phosphocreatine breakdown and its impact on energy availability is very important and suggests that creatine supplementation may be very crucial for such athletes. So this is basically the schematic flow of the phosphagen system. As already earlier explained, the initial energy burst occurs in a short burst of intense physical activity, such as a sprint or a heavy lift, and the body requires a rapid supply of energy. So the initial source of energy here is the ATP that is stored in limited quantities within muscle cells. And ATP is generally referred to as the body's energy currency because it provides immediate energy for cellular processes. And once the ATP is depleted, you find that phosphocreatine can regenerate more ATP. The role of phosphocreatine. As ATP levels decrease, the body turns to creatine phosphate for additional energy. And this is what I've been stressing. Once the ATP has been depleted, the phosphate creatine or creatine phosphate, it becomes very important in order to generate more ATP. So this creatine phosphate is a high energy molecule that is stored within muscle cells alongside ATP. And it serves as an energy reserve because it can quickly donate a phosphate group to ADP, that is adenosine diphosphate, in order to regenerate ATP. ATP regeneration. Once the ATP is depleted during intense exercise, creatine kinase, an enzyme, facilitates the transfer of a phosphate group from creatine phosphate to ADP. So this process regenerates ATP and allows for continued muscle contraction and the maintenance of power and strength. Some limitations of the phosphagen system. This system is highly effective for providing immediate energy, but it has limitations in terms of duration. The longer the exercise takes, the less important this system becomes. So it can sustain high intensity efforts for only a short period of time, typically up to 10 seconds. Beyond this time, the body has to rely on other systems, such as the glycolytic system, in order to meet energy demands. Recovery and replenishment during the phosphagen system. After this intense activity, there will be a period of recovery during which ATP and creatine phosphate levels are replenished. And creatine supplements are sometimes used by some athletes to enhance their stores and improve performance during repeated short bursts of intense exercise. The glycolytic system. This one is the anaerobic system that does not require oxygen. The main fuel here is glycogen, that is stored form of the glucose and also glucose. The duration of exercise or energy, it can occur from short to moderate bursts of high intensity activity. After those 10 seconds to about 2 minutes, the glycolytic system becomes very important. And some of the exercises that require the glycolytic system are short distance running, swimming sprints, and powerlifting. The process. When the phosphagen system can no longer meet the energy demands, the body turns to glycolysis, and this process breaks down glycogen or glucose into ATP. And the process occurs in the absence of oxygen. That's why it's called anaerobic system. And this leads to the production of lactic acid, which can cause muscle fatigue and soreness. So, in the glycolytic system, Glycogen is converted via glycolysis to lactic acid, and this process generates ATP. Then the oxidative system or the aerobic system. This one, the main fuel here is carbohydrates, fats, and also to a lesser extent proteins. Duration of the energy. This one occurs during long durations and lower intensity activities. Any activity that will exceed now the 2 first minutes or more, we shall require the oxidative system. Examples of such exercises include long distance running, cycling, swimming, and endurance events. The process. During sustained exercise, the body relies on oxygen to produce ATP through the aerobic metabolism of carbohydrates and fats. And this process is highly efficient and can sustain energy production for extended periods. It also produces less lactic acid and is less fatiguing compared to the anaerobic energy pathways. So this is basically a diagram that represents the oxidative system. The interplay of energy systems. You find that in most sports, activities do not exclusively rely on one energy system. Instead, there is usually an interplay between these systems. For example, during a 400-meter sprint, primarily the athlete utilizes the glycolytic system from about 0 to 10 seconds. But as the race progresses, the oxidative system becomes more important during the sustained long periods of exercise. Longer endurance events such as marathons mainly also depend on the oxidative system. But during sprint finishes, athletes may have to tap into the glycolytic system for a final burst of energy. So this is basically what we had for the first lecture of Introduction to Sports Nutrition. Thank you.